Okay. So thank you so much, everyone. Welcome to OneQuantum Africa meetings. My name is Farai Mashandu. I'm the president for OneQuantum Africa. So OneQuantum Africa is a platform where we bring people from industry, from academia, from civil society, and from business together to learn about quantum technologies and figure out where we are and what we need to do and the best way to think about these technologies as they evolve. Today, we are so glad to have Professor Will Oliver from MIT. He's the professor of electrical engineering and computer science, as well as physics at MIT. And I'm going to give you more details about him briefly before he comes through to present. So let me just introduce the platform and pay the bills, as it were. We also thank our sponsors, our African sponsors, Vieta Quantum Technologies, headquartered in Johannesburg. And at Vieta Quantum Technologies, we believe that the lives of ordinary Africans can be made better by adopting smarter solutions to everyday problems. So we thank them so much. They are the ones who pay for our Zoom platform and we pay for the operational costs that go into making all these events possible and to produce our videos that we make available on our YouTube playlist. We are always happy to hear from more partners, to collaborate with the partners across the world and in Africa, especially to move technology forward. At OneQuantum Africa, just to briefly give you an indication of what we do, our work focuses on 4 pillars, which are communities where we gather leaders in the continent and connect them to the global quantum tech ecosystem through events like this one, where we invite experts from across the globe to come and share with us about quantum tech and give us a feel of where we are and how to think about this emerging technology. We also do summits, and we've got many other community events which we facilitate and initiate in order to connect people and make them collaborate, learn, and exchange. We also do mentoring. Recently partnered with Keysight Technologies to offer mentoring to each and everyone who's interested across the world. And currently, we have got more than 300 people who are signed up, with about more than 100 mentors as well, offering their time and giving professional advice and guidance to mentees. We also do have careers where we advocate for underrepresented communities to be given opportunities for internship and employment. And we also work with career partners to facilitate growth of these underrepresented minorities whenever they're hired so that they are set up to succeed. We do projects. We have recently partnered with Strange Works, which is a startup out of Texas, which has given us their access to their platform where we collaborate with our communities to work on projects that are relevant to local conditions. Our platform at OneQuantum Africa brings quantum tech leaders from the continent and connects them to the global community. And these are some of the faces that have, that have come forward to present on our platforms, and we're really, really so glad. And we've been growing so fast in Africa, and I think I should just mention that quickly, that we now have got chapters, almost 9 chapters and counting, within Zambia, in Ghana, in Nigeria, in Rwanda, in Cameroon. And of course, we have had these chapters, 4 more chapters, which are Zimbabwe, South Africa, Libya, and Kenya. So those ones have been with us for a while, and we have added more, and we keep on expanding these efforts. If you've got a country that is not represented, please reach out to me, and I'll be happy to facilitate and to make sure that we've got a chapter in every country in Africa and move quantum tech forward. Right, let me mention quick opportunities that I think I want to highlight quickly. Our colleagues at Quantum Leap Africa are going to be offering what they call the Quantum Quest training program. This is open to all Africans, and they've partnered with the University of Amsterdam and QSoft in the Netherlands in order to offer this. Please take advantage of this opportunity. We are happy to see more partners, coming up in Africa and providing content and resources to support the development of quantum tech in Africa. Qubit by Qubit is also offering an opportunity for high school teachers and educators to come on board and facilitate the access of quantum computing to high scholars. Azure Quantum which is a program by Microsoft, is also calling for applications from the continent for those who want to access devices that they have available. I think they have the Honeywell device, they have Honeywell, they have IonQ and others, and you may have access to these platforms. Please, reach out to me and let's discuss your goals, and I can help you to make those applications if you need to, and I can share those details as well on how you can access their platform and do applications. IBM brings us the Quantum Challenge in Africa this, I think, on the 9th of September, if I'm not mistaken. I can share more details. I'll share the links. So please, this time around, the challenge is focused on end users. So I encourage people to give it a try, to come on board and just to look at the kind of problems they are making available and how to think about solving problems using quantum computing. I think it's a very important event to join, and it will make you have a practical feel of the opportunity for quantum computing in problems that are relevant in the African context. So I'll share details about those opportunities. Brings me to introduce our speaker today, who's not easy to introduce by any measure, well accomplished in the field, and he's done a lot of amazing work to move quantum tech forward, especially in superconducting quantum computing. Professor Will Oliver is the principal investigator in the Engineering Quantum Systems Group at MIT. He also is with the MIT Lincoln Laboratory. He provides programmatic and technical leadership targeting the development of quantum and classical high performance computing. There's a lot that I can say about him, and I will leave him to perhaps add to this introduction because it is a mouthful. And today, I think I requested him to share with us on the developments in nanoscience and engineering that are important in the process or in the journey to realize a capable, or what we could call a universal quantum computer, which promises to deliver very interesting value to a lot of our challenging problems. Let me also talk about what's going to happen. We are now doing bi-weekly meetings, so it means that we are going to have another meeting on the 22nd of September at 7 p.m. CAT. And this time around, we have Celia Metz-Baker from the Quantum Economic Development Consortium. She's the executive director there, and she's going to come and share with us about the quantum tech ecosystem, which I think is a very important, meeting you don't want to miss. So let me stop sharing my screen to share with us his thoughts. Yeah.
Great. Thank you so much, Farai. That's really. Oh, yeah.
It's okay. You can proceed. Unfortunately, my screen here was frozen, but I think you can take it forward.
Okay, sounds good. Let me know if this looks okay. How's that?
The screen is coming up. I'm not sure if other people can see it. My network may be giving me issues a bit here, but yeah, I see the screen now. You could go full screen.
Okay, how does that look? All right, well, yeah, let me know if there's any issues with this. Hopefully this is looking okay on your side.
So you could just check the chat.
I'm sorry?
Because I may have issues with my network. The chat may be...
Rai, your voice is breaking.
I see two screens for some.
Yeah, can somebody? Screen is amazing. Okay, great. I'm gonna proceed then. Thank you very much, Farai, for that introduction. I think there was some bandwidth issues there for a few minutes, so I didn't quite catch everything. But yeah, I'm really happy to be here. Thank you for the invitation. It's great to see OneQuantum Africa and all these activities that we just heard about from Farai. What I'd like to tell you about is quantum engineering of superconducting qubits. That's what I work on here at MIT. And before we get into quantum computing, I think it's worthwhile to go back and remember the history of classical electronic computing. So the vacuum tube, as you remember, was invented in 1906, and it was used for radio transceivers for many years. In fact, almost 40 years before we saw the first vacuum tube-based computer called ENIAC, which I'm sure you've heard of. That was developed at the University of Pennsylvania in 1946. Now, the following year, Bell Labs invented the transistor. And although about 10 years later, we had a fully transistor-based computer called TIXO, or TX0, it didn't look anything like the computers we're using today. It was basically three-legged transistors soldered together in configurations that made a computer. Of course, we needed the integrated circuit to move forward. That was in the late 50s. And then in the 1970s, we started to see processors built with integrated circuits, such as the Intel 4004, which is a 4-bit processor, only about 2,000 transistors. Fast forward another 20, 25 years to get to the Pentium Pro with millions of transistors, and then another 20, 25 years to get to where we are today with multi-core processors, billions of transistors, and also graphical processing units. So from today's standpoint, looking back to the first fundamental logic element, well over 100 years of development. In comparison to that, quantum computing is still relatively young. In the early 80s, Richard Feynman, Uli Mannin, and others suggested that if you want to simulate a quantum system, we should use a quantum system to do that, basically proposing a quantum computer. And theorists thought about it, and it took about 15 years to get to the first practical algorithms, such as Peter Shor's factoring algorithm, or Love Grover's search algorithm, right? As well as the first theoretical foundations for quantum versions of error correction. Eddie Farhi and Nishimori talked about quantum versions of annealing, quantum annealing, and adiabatic quantum computing. In the early 2000s, Ike Chuang and colleagues at IBM factored the number 15 into 3 times 5 using Peter Shor's algorithm, showing that it works. And fast forward another 20 years to where we are today, and we have quantum computers, small, but quantum computers in the cloud from IBM, Google, and others. And Google has even demonstrated that a quantum processor can outperform even the best classical computer in the world for a certain task. So the takeaway here is that quantum computing is transitioning from scientific curiosity to technical reality. That's happening right now. But we also know that advancing from fundamental discovery to useful machines is going to take time. And of course, it also takes engineering. And that's what I'd like to talk about today. Now, of course, another takeaway here might be that you should be in the game if you want to play in the future. It's maybe no surprise that many of the companies that are advanced today in developing these classical processors were in it from very early stages of the technology development. So with that as an introduction, let me talk about an outline. I'll give a brief introduction to quantum computing, what it is. I'll then talk about, in particular, superconducting qubits. We'll then talk about engineering quantum systems, what error correction is, how it works. And then at the very end, I'll talk a little bit about my own research with 3D integration. So just a background, getting on the same page. Classical computers, we know, work based on bits of information. That could be a transistor's voltage, high or low. It could be the spin of a magnetic memory. Here, the states are either 0 or 1. That's it. They're discrete. And when we make a measurement, as long as there isn't too much noise, when we set this bit as 1, we'll measure it as 1. When we set it as 0, we'll measure it as 0. Now, of course, quantum computers are different. They work on something called quantum bits or qubits, which is a coherent, quantum coherent 2-level system. And the way we can think about it is in terms of this block sphere, but you can think of it as the planet Earth. At the North Pole is state 0. At the South Pole is state 1. And when you're at the North or South Pole, you're basically one of these classical bits. But of course, we can be anywhere on the surface of the Earth, and so can the qubit. And if you're anywhere other than the North or the South Pole, the qubit is in a superposition state of 0 and 1 simultaneously with these weighting factors alpha and beta. Now, I want to emphasize that it's one position on the planet Earth, meaning that it's one state, but the state has properties that look like 0 and 1 simultaneously. This is called a superposition state. And if, for example, we were on the equator where we have an equal weighting of 0 and 1, when we make a measurement, probabilistically, we will snap back to the North Pole and see state 0 50% of the time. And 50% of the time we'll snap to the South Pole in state 1. So measurement is probabilistic in a quantum system. So then the upshot is that quantum computers encode information in a fundamentally different way. And the implication for that can be seen here. So let's jump back to a classical computer. If you have a bit of information, or let's say you have n bits of information, you can form an exponentially large number of states, so 2 to the n, in fact. So if n is 3, you'll have 8 different states, 0, 0, 0, 0, 0, 1, etc. But you can only represent one of them at a time. Okay, so if we want to calculate with an input 0, 0, 0, we input that into our classical computer and it calculates some output. If we want to have a different input, we basically have two choices. One is we can do what's shown here, which is we can reproduce copies of the hardware and feed an input state into each one. Or you could take a single computer and serially in time input different states at different times. But either way, if there's an exponentially large number of states to go through, it's going to take either exponential hardware or exponential time. Now, quantum computers also have n bits, and they, in principle, can be organized into 2 to the n different components, but you can represent in a superposition state all of these components simultaneously. And so that's represented here with weighting factors, alpha, beta, gamma, etc. And what this leads to is a situation where you can input a quantum superposition state into a quantum computer and get an output state with different weighting coefficients. And I'll talk about that a little bit more. But basically what happens inside here is not that every one of these input states is calculated in parallel. That is not what happens. But through a process of quantum parallelism and quantum interference, most of these coefficients will go to 0. And the output that, in fact, represents the answer to the question we're posing, that weighting coefficient will go to 1, right? And so the right answer gradually coalesces and is the only one that you measure. That's basically the idea. So how do we take advantage of quantum information? Well, we have to control it. And if we go back to our classical computing case, you've probably seen, at least if you're an electrical engineer, many of these symbols, which represent classical Boolean logic gates. And so this one is the NOT gate, there's an AND gate, an OR gate, etc. And the truth tables are shown here. I won't go through it, but the main point I want to make is in classical Boolean logic, if you want to run an algorithm, you basically only need a handful of these gates. So for example, the NOT gate and the AND gate together form a universal set. You could also choose NOT and OR. There's a whole bunch of different combinations, but with a universal gate set, you can implement any Boolean logic on a classical computer. Quantum computers are the same. There's a number of gates that we can perform. They're listed here. And for example, the X gate represents a rotation of the qubit state around the x-axis. We'll see an example in a minute, but there's a handful of single qubit gates that rotate around different axes. And then there are a couple 2 qubit gates where the rotation of qubit A depends on the state of qubit B. And the point is that with just a handful of these gates, not all of them, a handful, such as this one here, one can perform arbitrary quantum logic, any quantum logic. And it's worth saying that, in fact, you can perform any Boolean logic on a quantum computer as well, but quantum computers aren't that good at doing that. And in fact, if you try to run a Boolean algorithm on a quantum computer, it's basically no better than running it, and in often cases it's worse than running it on a classical computer. Okay, So let's dig in a little bit to this gate model approach. Classically, we had this inverter take state 0 to state 1. It could take 1 and turn it into a 0, just inverts. And the quantum analog of that is called the X gate. And it takes quantum state 0 to quantum state 1. And this notation here is just put around the 0 and the 1 to say that it's quantum. This is what it looks like on the planet Earth, or the block sphere as we call it. The blue arrow is representing the qubit state, and it starts at the North Pole, and it rotates to the South Pole under the action of this pulse, which is represented, the envelope is represented by this red arrow coming in and out, and it's along the x-axis, right? That's why we call it an X gate. So this takes state 0 to state 1, state 1 to state 0. That's basically an inverter. And remember, if you're at the North or South Pole, you're just classical. So this is no different than the classical gate. But where it gets interesting is that you could start anywhere on the surface of the planet Earth. You don't have to start at the North Pole. And if you start in any position, doesn't matter where, this gate will also rotate 180 degrees around the x-axis. And what it does, if you look at this notation here, the superposition state with weighting alpha and beta, it swaps alpha and beta. That's the action of this gate. Okay. So this is just one example of a single qubit operation and how we can change the state of the qubit. So now let's think about an example of a 2-qubit gate, and here we'll think about the controlled knot. Its classical analog is called the exclusive OR gate, or XOR gate. And there are 2 input bits. These are classical bits, X and Y. One is a control bit, and the other is a target bit. And what comes out is the exclusive OR operation, and the truth table is shown here. Now, the way to think about this is that when the control bit X is in state 0, nothing happens to Y. It's basically just passed to the output. But when the control bit is in state 1, now we implement a NOT gate on bit Y. So 0 becomes 1 and 1 becomes 0. Okay, so it's a controlled NOT gate. Now that's the classical version. The quantum version is written with this notation, where qubit X is the control, qubit Y is the target. We call it C0, controlled NOT. If you look at the truth table, it's exactly the same as the one that we just described on the left. And so the rotation or the operation on qubit Y, the target qubit, depends on the state of qubit X. Now this leads to a very interesting type of quantum state. In fact, these are called entangling states or entangling gates for the following reason. So if we have an input state, and we'll say that our control qubit is in a superposition of 0 and 1, and the target bit is in state 0, we basically can follow the rules of linear algebra and take this one step at a time. So first off, these 2 terms, quote, multiply together. And so if the control qubit is in 0, we don't change the target qubit. So that term comes down here. And then we can add to it these 2 terms. And when the control qubit is in 1, we know we need to flip the target qubit. So this becomes 1. And now this is a very interesting state, because we can't factor it anymore into something that looks only like X qubit and only like Y qubit. We could do that up here. Here's the X part, here's the Y part. But once we've implemented the quantum C0 gate on this input state, we can no longer do that. And in fact, the reason we can't is related to the fact that this is an entangled state. It can't be factored. And in fact, under any rotation, single qubit rotations, it can't be factored either. Okay. So this is an example of a 2-qubit gate. And again, a handful of the 1 and 2 qubit gates together can form a universal set of gates, making a universal gate-based quantum computer achievable. Okay, so of course we have to build one, but this is what's behind it. So then we want to run an algorithm using these gates, and this is what it looks like. I mentioned that we'll start with a massive superposition state, and in fact, we generally will equally weight it. I'm ignoring the normalization here, but we equally weight this superposition state, comprises all 2 to the n states. And according to some prescription or algorithm, we will perform single qubit operations. And the thing to notice is I'm applying this operation to qubit 3 in this case, but in fact, it's affecting the coefficients on all 2 to the n components of this state. right? That's quantum parallelism. Now that's followed by quantum interference. And what the net result is that these coefficients have changed. These weightings have changed. Now we'll sometimes run some coupled qubit gates where again, a rotation on qubit A or qubit 1 will depend on the state of qubit B. And again, you apply it to qubits 1 and 2, but it affects every component in the superposition state. Again, quantum parallelism, followed by quantum interference. And at the end of the day, the goal is that the output state that represents the answer has all of the weighting or probability amplitude, as we call it in jargon, coalesces to that one state, so that when we make a measurement, we get that result. And the reason is that our measurement is probabilistic. And the probability that we measure any one of these components goes as the magnitude squared of the coefficient. So if this coefficient is 1, then with probability 1, we'll measure the right answer. That's how it works. So that's the challenge for an algorithm designer, is to come up with a sequence of single and 2 qubit gates that enables this to happen and solve a problem that we care about. Okay, so if we can do that, then we might be able to get quantum advantage, right? And here are the ingredients. So first of all, there better be no fast, efficient classical algorithm to solve a problem, because if there were, we'd just use these great classical computers we already have. The second thing or ingredient is that we need to also have a fast quantum algorithm that's efficient, right? I guess that's obvious. And the third is that we'd like it to address a useful problem. And so the overlap here is today rather small. There's only a small region where we know of useful quantum algorithms that exist. But a lot of people are working on trying to expand that region. And when we think about quantum advantage, there's really 2 types that we think about. One is the prefactor, and one is in the exponent. So if you improve the prefactor, that's some polynomial function of n, we say that that's a polynomial improvement. One example, say, is quadratic improvement from Grover. Something that scales as n goes to n to the 1/2 power, square root of n. Okay, so that's powerful, but certainly not as powerful as an exponential improvement, right? And if you reduce this exponential dependence on n to a polynomial, this is really fantastic. So something that goes as 2 to the n, if you can reduce that, for example, to n cubed, that's a substantial improvement. And I didn't mention it, but n represents the size of your system, how many resources, what you're representing, et cetera. Okay, so exponential growth is really fantastic, and we don't usually see it in everyday life. One example that I like is this problem or riddle where your boss tells you he'll pay you in pennies rather than your salary for a month. And here's how it works. We'll double the number of pennies I give you every day for a month. And so on the first day, I'll give you 2 to the 1 pennies. Now this poor person is going to work every day, Sunday through Saturday. Okay. Guess he wants a lot of pennies. On the second day, he'll get 4 pennies, or she'll get 4 pennies. On the third day, 8 pennies. And if you think about this, you know, you might say, well, that's increasing, but I can't believe that's ever going to be, you know, very large at the end of the day. And your regular salary is $1 million a month. You might say, I'm going to take $1 million or $10 million. Let's even say that. So after 31 days, would you take the pennies or the $10 million? Right? And a lot of people would say, I can't imagine these pennies would ever be worth that much, so I'm going to take 10 million. But in fact, if you added it all up, it would be greater than 21 million, because just on the 31st day, you get enough pennies for $21 million, right? And this is the power of exponential growth. And you could think of these days as qubits, right? And the growth that they give in terms of power. So if we have a 30 qubits quantum computer where these qubits are perfect, that's a very important caveat, but if these are perfect qubits, you could simulate that quantum computer basically on a laptop. It would take your entire laptop to do that. If you had a system of 50 qubits, now you need a supercomputer, right? 80 qubits, and basically you'll need all the computers on Earth. 160 perfect qubits, now we're talking about all the silicon atoms on Earth just to store that information. And then 300 perfect qubits, well, that's all the atoms we have in the known universe to just serve as the memory to keep track of all of those coefficients, right? So this is really an example of exponential growth in power that is the promise of quantum computing. Now we have to realize that promise. Okay. So quantum algorithms and speed up, I won't read through this whole chart, but on the algorithm side, there are a number of algorithms: simulation, factoring, solutions to linear systems of equations, optimization and search. And you can see here their classical time and their improved quantum time, whether it's an exponential improvement or quadratic improvement. Now, there are limitations, and people are still doing research to improve these algorithms in anticipation of hardware getting large enough in the future that we could actually run these algorithms on a problem that we care about at a size we care about. Many of these algorithms have been demonstrated, but on a small quantum computer where there's no advantage over classical computing, right? You could just very easily do the same problem on a classical computer. Okay. So why don't we have such cute quantum computers today? And there are two times that are the reason. And one is coherence time. And that's basically the qubit's quantum lifetime. If you have a quantum state, put it in state psi at time t equals 0, it's perfect. We know exactly what it is. As soon as we start our stopwatch, it's interacting with its environment. And over time, that state decays or it blurs and eventually becomes lost. Now, the qubits that represent the state, they're not lost. They're still there. But the state that they represent is no longer known to us. It's in some other state that we don't know because we don't have control of the environmental degrees of freedom. And the lifetime over which this happens is called the qubit's lifetime. Now, the second time that we care about is called the gate time. And this is the time required for a gate operation, say a typical single qubit gate operation. How long does it take me to go from the North Pole to the South Pole? And the figure of merit, of course, is then how many gates can I do before I lose my state within the coherence time, right? That's the figure of merit. Okay. It's worth noting that long coherence times, while good, are not sufficient. And the reason is because of the number of gates before an error. Many systems that have long coherence times also have long gate times. And so the ratio is not so different. So if we want to visualize this, different modalities against one another, we can do that on a chart like this, where on the vertical axis, we have the number of operations before an error. And that's basically 1-to-1 in what we would call the gate fidelity. So if it's one error in 100, that's 99% fidelity. 1 in 1,000 would be 99.9% fidelity, et cetera. And then on this horizontal axis is the gate speed. And this is in frequency, so it's 1 over the gate time. Now this dashed line that just appeared is the lowest threshold, rough, it's approximation, to perform quantum error correction. So error correction, as we'll see, is basically aggregating physical qubits together such that together as a single unit, they perform better than any of the individuals. And of course, as you might imagine, the individuals need to be at least so good or at least sufficiently high quality so that when I add more of them together, things actually get better. And to do that, you need to be above this line. And the further above, the better. The less you need, the fewer qubits you need to achieve this improvement. And then of course, the best performance is in the upper right corner. So there are many modalities that have demonstrated 1 qubit gates, and they're currently demonstrating 2 qubit gates. Many of them have demonstrated it, and I should update this chart, but we're looking for benchmark results where it's benchmarked in the proper way. And then there are a number of modalities which have demonstrated both 1 and 2 qubit gates, meaning they could in principle form a universal set of gates. And there are many that you see here. One of the leading modalities today is trapped ions. Here are some of my colleagues at MIT working on that. And another one is my own research in superconducting qubits, along with my colleagues here at MIT. If you ask me what we're trying to do, the trapped ions are basically trying to get faster, right? They're about 1,000 times slower than superconducting qubits. So they want to be faster, and they also want to improve the fidelity of their 2 qubit gate. Superconducting qubits are already quite fast, and we're trying to get higher fidelity gates. And some of the other modalities, neutral atoms, here's some colleagues there, nitrogen vacancy centers in diamond. Here are some colleagues at MIT. Now, NV centers can be used as quantum computers, but they really shine as quantum sensing technologies. And then I'm starting a silicon quantum dots effort here at MIT this fall. So those are the major modalities and how they stack up against one another. Many candidates, trapped ions and superconductings are probably considered in the lead right now, but of course this technology will evolve and unfold over time. Oh yeah, and I just want to mention that many of these 2-qubit gates have seen improvements since I made this slide a couple of years ago. So those arrows indicate that. Okay, so that's basically the introduction. And now let me move on to just a few slides on superconducting qubits. So a superconducting qubit is basically an electrical circuit that looks like an atom, behaves like an atom. So if you take an inductor and a capacitor and put them in series, you make a resonator, an electrical resonator, and it has a parabolic potential shown here. And if you cool this down to a low enough temperature where the energy scale Boltzmann's constant times temperature, kT, is much less than Planck's constant times the resonance frequency of the circuit, well, then you'll have a quantum object. It has discrete energy levels, and you can label them 0, 1, 2, 3, etc. Now, this isn't so useful as a qubit because the separation in frequency or energy between 0 and 1 is the same as between 1 and 2. And so we can change that by making one of these elements nonlinear. And here we could choose either one, but we have a convenient way to make the inductor nonlinear, and that's to introduce something called the Josephson junction. It's a tunnel junction, meaning that there's an insulator, and on each side of that thin insulator is superconducting material, typically aluminum. And so, the charge carriers can tunnel through that insulator. It has current and voltage characteristics here, which I won't go into, that were identified by Brian Josephson in the 60s, but you can combine them together in the usual way to define an inductance. And the upshot is that that inductance is highly nonlinear in the current that's flowing through the junction. Okay, so it's a nonlinear inductor. When we put that nonlinear inductor in parallel with a capacitor, we now have a different potential profile. In this case, it turns out to be exactly a cosine. And as a result, the level separation between 0 and 1 is distinct from 1, 2 transition, 2, 3, etc. So we can basically uniquely identify the 0, 1 transition, and we'll call that our qubit. And all superconducting qubits basically work this way. This is the simplest example called the transmon, but different qubits can be made by adding more capacitors or inductors or additional junctions to achieve some advantage at some trading off some other property, right? We can engineer them. Now, we typically choose that qubit transition frequency to be 5 gigahertz. That's a choice, and it's convenient because it allows us to use a lot of existing microwave equipment to control our qubit and do those rotations around the planet Earth that we talked about. But it has an implication for the temperature at which we operate the qubits. 5 gigahertz, if you equate that to kT, the temperature would be 250 millikelvin. So that's cold. And we want to be much colder than that so that thermal energy doesn't just excite my qubit. So we operate at about 20 millikelvin. That's about 100 times colder than outer space. And it sounds esoteric, but in fact, these are commercially available machines today. You can buy these refrigerators off the shelf. And what you're seeing here is the coldest level of a dilution refrigerator. Now, it's not cold now, it's open to the air, but this plate is at 20 millikelvin or 10 millikelvin, something like that. And everything below it is also at the low temperature. And you can see many common items in here like filters and coax cables and switches, et cetera. All of that is to get the signals where they need to go to the qubits, which are inside these small packages. Now, of course, we have to fabricate these devices, but that's actually a feature. Superconducting qubits are built on silicon wafers. It's a silicon technology using silicon fabrication tools. So we fabricate here on 8-inch wafers, so 200 millimeter wafers. If you zoom in on any one of these devices or chips, you can see here 5 qubits lined up in a row. These wiggles to the upper right are resonators that we use to read out the qubits. And from the lower left, you see some lines that are used to control the qubits. If we zoom in on one of these, you can see this plus sign. That's a capacitor, actually, a capacitor to the ground. And if you zoom in even further, you can see the inductor. Now, this inductor is made of two junctions that form a loop. And that loop is convenient because if we put magnetic field through that loop, we can actually tune the qubit's frequency. It's not fixed at 5 gigahertz, but we can tune it down, and in some cases up. And if we zoom in even further, we can see one of these Josephson junctions. This is what it looks like. Here's aluminum, and in between these two, where it overlaps, is a thin layer of oxide that forms the junction. So we fabricate these on silicon. We do that at fabrication facilities, two of which are pictured here. One is at Lincoln Laboratory, and the other is at the MIT campus. And I mentioned that we like to use microwave control. We pick 5 gigahertz because it's convenient, and we're using equipment like this. And what I'd like to show here is basically how we control it. So in electrical engineering language, we do IQ mixing, in-phase and quadrature mixing. We take a local oscillator, which is close to 5 gigahertz, and this mixer will multiply it by some lower frequency pulses with an envelope. And they'll go to either the I or the Q port. I is in phase, Q is quadrature. And the difference is that the quadrature port shifts everything by 90 degrees relative to the I port. And so we can associate that with the x-axis and y-axis of our block sphere. So you see this going along. The first thing we're going to do is an X pulse of 180 degrees. And so that's rotating around X. That's using the I port. Here's minus X, so rotates back. We're now going to switch to the Q port. And now we're rotating around the Y-axis. Now, if the pulse has half the area, it only rotates half as far. So we went to the equator. And now we can go back up to the North Pole. And so this is how we can use microwave pulses and mixing techniques to operate on the block sphere or the planet Earth. And if we look over the past 20 years or so, what we've really seen is that the properties of these qubits have improved dramatically from a nanosecond back in 1999 to well above 100 microseconds today. And this is from a combination of materials science, fabrication engineering, and design. And so here are some of the times that we're achieving here in the qubits we make at MIT for different types of superconducting qubits. And if you'd like to learn more, here are some review papers over here on the right. So of course, today, this is what a superconducting processor looks like. Here's Google's Sycamore chip. Here's IBM's, I think this is a 16 qubit chip. This is a chip from Rigetti, a startup company. This is the backside to an Intel chip. These are all gate model. This is a D-Wave quantum computer that's used to do quantum annealing, a different type of quantum computer. But all of these, of course, this in the center is not a quantum computer. This is, as you might know, the Wright Flyer, flown by Orville and Wilbur Wright back in the early 1900s. It was the first manned, self-propelled flight enabled by some improvements in control, actually. And it flew maybe 600 feet, right? It didn't fly very far, but this was a demonstration that flight was possible, right? And it foreshadowed many things to come in aviation, right? And I think that the recent Google demonstration of quantum advantage in their Sycamore chip is very much like this, right? It's a significant milestone. So there's a lot of promise to quantum computing, but if we want to realize that promise, we need to engineer quantum systems that are robust, reproducible, and extensible. So let me talk a little bit about engineering systems at a high level. Of course, if you want to engineer a system, you need to have an architecture. And one here, due to Cody Jones, has, of course, the application in the human-computer interface at the top. The physical qubits are at the bottom. And then in the middle, you see many pieces that are probably familiar from classical computing. Of course, there's a logical controller. It has a compiler. It interprets the computing programming language the user's using and implements them into gates that we would apply to our quantum computer. Now, there's two other layers that we need to have, and those are active and passive error suppression. Now, you've probably seen memory modules that are error corrected. So that's an example of classical error correction. There's quantum versions, and I'll give an example of this in a moment. They're also in passive error suppression techniques where we just do things that we know are good to help reduce the error rate. And on every clock cycle, a quantum computer needs to do both passive and active error correction, or at least detection, error detection, as well as implement the algorithm on the physical qubits. That's basically what it looks like. And what I'd like to do now is give a few examples of each of these first three layers, physical, passive, and active error correction, using a sport that is called lacrosse. And maybe you've seen this sport before. The players hold a stick with a basket at the end and a ball. You can see the ball in there. The goal is to keep the ball in the basket as you run down the field and eventually throw it into the opponent's goal. So I'm going to show a video now, and I hope that the bandwidth is sufficient to get the idea of what's going on. But this is a lacrosse player, a young lacrosse player, and he's got the basket and the stick, and the ball is here, and he's going to show you what you should not do. These are the physical qubits prone to error. And of course, as he runs along the ground, his running is going to create noise. You could think of it, he's bouncing, as well as the ground is not perfectly flat. And so this is what it looks like. So he's running, but as he runs, he's bouncing, and that ball is going to fall out very quickly, right? These are physical qubits. Physical qubits are subject to errors due to their environment. That's just the way it is, and we have to do something about it. So one thing that we can do very easily is passive error suppression. So this is doing an action which we know will reduce errors. We don't measure anything, we just do it. In lacrosse, that's called cradling. You see this guy now running down the field, and he's cradling back and forth by 180 degrees with his wrist. He's not thinking about it, he's just doing it. But that decouples the noise of him running from the ball, and it keeps it in the basket. And then he can run down the field and throw the ball in his goal. Okay, that's an example of passive error suppression. And rather than, of course, doing this with his wrist, we apply pulses to the qubits. Now, even if you do that, you can't stop all errors. You get rid of some of them, but occasionally the defender is going to come up behind you and he just knocks the ball out of your basket. And when that happens, you have to do two things. One is you have to know that the ball fell out, the error occurred, and then you have to go and pick the ball back up again. So you actively, first you detect the error, you see where the ball went, you know what kind of error you had, and then you go back and physically pick it up again. You actively fix it. That's active error correction. And again, that's implemented with pulses in a quantum computer. So with that, let me just, in the last few minutes, show some pictures of what we're doing to help to 3D integrate these chips. So first off, these are some pictures again of our one of our chips. There's 5 qubits in a row. We saw that before. If we look at the coherence times of these qubits, it's about 100 microseconds. This is something called Ramsey. It's a T2 measurement of coherence. Doesn't really matter. What matters here is that it's decaying on a time scale of 100 microseconds. The gate time that you can compare with that is about 10 to 50 nanoseconds. Okay. Now, if we do benchmarking of the fidelities of our single qubit and our 2 qubit gates, single qubits are better than, we would say, 3 nines, so better than 99.9%. And our 2 qubit gates are almost 3 nines, almost 99.9%. So that's great. And now what we want to do is extend not just from 1 dimension, but to 2 dimensions. And here's a chip that we're measuring with 4 qubits by 4 qubits, so 16 qubits in total. And we're just learning how to do that. But one thing you can see right away is that there's a lot of control wires coming in from the edge, and this is not extensible. Like if I go to 5 by 5 or 6 by 6 arrays, I'm just not going to be able to bring in all the electrical signals from the edge without spreading everything out, right? And that just makes the chip bigger. This is not extensible. And so we're currently building a larger refrigerator. Well, we're buying the refrigerator and putting wires in it, but capable of 64 qubit measurements. So that's going to start with 4 of these 16 qubit chips, and as the chip gets bigger, we'll be able to measure it here. This is from a very generous donation from Keysight Technologies. Okay. But if we want to measure something like this and extend it, we're going to have to do 3D integration. It is bring the signals in from the third dimension. So what you see here, oh, it sounds like someone might have their microphone on. Yeah, thank you. Yeah. So what we do is, at least here, is we have something called a 3 stack, which is we take 3 chips and we stack them on top of each other. And there's some reasons to do that. The 3 chips are the qubit chip, interposer chip, and then a readout, a multi-layer readout and interconnect chip. So first off, these qubits are very sensitive to their environment. So anytime you stack things together, you want to make sure that the qubit is seeing the same kinds of materials as it normally sees. And it normally sees silicon in the qubit chip. And in this configuration, it will continue to see silicon. So that's one feature. The second is that we get another surface to place active elements. So we can put qubits or tunable couplers between on these 2 layers. So we get another layer to work with. Another feature is that we need to have what's called through silicon vias. I'll show a picture of this, but this is an electrical conduit that can bring signals from below to up here, where the qubits are operating. And then, of course, the final feature here is this readout and interconnect layer, which has multiple wiring layers that can go over and under each other, so that we can make this chip very, very wide and large, route signals where they need to go, and then when they get to the right place, the TSV or the through silicon via will bring them up to the qubit and then bring the signal back out. So that's basically what we do. Now, why we do it this way is because we can fabricate each one of these chips independently. They have different fabrication requirements, and it's much easier for us to do it separately than to try to do it monolithically altogether. Now maybe someday we'll learn how to do it all together, but today, if we do it separately, we get much higher coherence. So that's the reason. So this chip on top is, in fact, let's say this 16 qubit chip. You would take it and you would flip it over. It's called flip chip as a result, on top of the interposer. The interposer itself is, of course, silicon, and we etch very deep holes into the silicon. So they're 200 microns deep, but they're 10 to 20 microns in diameter. So the aspect ratio is 10 or 20 to 1. So very deep compared to their size. And they're lined with a material, titanium nitride, which also superconducts. That's shown here. The resistance goes to 0 below a temperature of 2 Kelvin. And of course, we're well below that temperature. We're 100 times colder. So this is how we bring signals up and down using basically superconducting wiring. And then finally, this bottom layer here is a multi-layer, also superconducting chip, which is made from another material, niobium superconducting. And what you see here in the light gray are different wiring layers, each one isolated from the other, so that signals can pass over and under. And where they come together, we call that a via. So we can go from one layer to the next layer, to the next layer, to the next layer. Now, it turns out that this process also has Josephson junctions, and we can use that for classical digital logic. There's a classical superconducting logic family, and we can use that for such logic. And we can use it for creating amplifiers. So for example, broadband, very low noise amplifiers that we may want to use to help read out these qubits. So that's another feature of using this. Although today we just use it for routing signals, but it has this potential in the future. So last slide. We started the talk by thinking about quantum engineering or engineering quantum systems, and it's really a new discipline. And that new discipline called quantum engineering comprises both science and math. If you want to think of it as an institute, this would be the School of Science, right? And the School of Science is not done for quantum, absolutely not. There's a lot of work still to do, but these computer scientists, mathematicians, physicists need to pivot if we want to build quantum testbeds. And at the same time, we need the School of Engineering to stand up and train engineers how to take their deep knowledge set, analog and digital circuit design, control, materials, etc., and pivot that from classical applications to quantum. So both sides pivot to build quantum test beds and ultimately future quantum systems. And so from my perspective, this quantum engineering is the bridge that connects science, math, classical engineering together, builds the abstractions that we're going to need so that we can efficiently make future quantum systems. And so with that, let me conclude and acknowledge many colleagues. The pictures don't show everybody. I think I've tried to list everybody here, both at Lincoln Laboratory as well as at the MIT campus in the Engineering Quantum Systems group. Let me also recognize our many sponsors, and let me thank you also for your attention. Thank you.
Thank you so much, Will. And perhaps we will take questions now. There were a number of questions that came through the chats as you were presenting. I guess it's time to bring them up. So let me just go to the chats and try to pick on those.
Okay.
Okay, so let me start with the first one. So John Barnes was joining us from the UK. He has got a question. So the difference and similarities between qubits and qubits are fascinating. Would you be able to expand on this just briefly?
Yeah, sure. So qubits are two-level systems, right? And so the scaling in terms of the state space is basically 2 to the n. But if you wanted more, a larger state space with fewer physical resources, you could use a quantum system that had not just 2 states, but 3, 4, 5, etc. And when it's 3 states, we call that a Q-trit, TRI. And when it gets more than that, we give up and we just call it a Q-dit with D, right? Meaning D levels where D is greater than 3. And the advantage is that you get, for 1 qubit, you get a much larger state space. Of course, there's no free lunch. And so the disadvantage is there are more decoherence channels that become present in the qubit. But certainly it's very interesting because, you know, as we know, these qubits or qudits are very sensitive to their environment, and having fewer of them, each one having, you know, a larger state space that it can occupy, may provide some advantage, particularly in these early years, but also maybe in the out years. And so it's another representation of quantum information that we can use. Yeah.
Okay, sounds good. I see the trade-offs there, very interesting. So Gibbs, the question, can you tell us why it is not better to perform a Boolean algorithm on a quantum computer than a classical computer? I ask the question because in 1996, Grover proposed a Boolean algorithm which is quadratically faster than classical algorithm.
Yeah, so I think that the 1996 Grover search algorithm, I'm not sure I would call that, if that's what you mean, I wouldn't necessarily call that a Boolean algorithm. Maybe I'm misunderstanding the question. But what I can say is that if we want to perform Boolean logic on a quantum computer, we're basically just reproducing the Boolean gates, right? And representing it on the quantum computer, right? And this could, you know, in some sense, right, you can think of a quantum computer as a reversible, it is a reversible computer. And so you could do Boolean logic, you can do reversible Boolean logic. But the point is that there certainly is not an exponential speed up by doing that. And in fact, by using the quantum gates that we have to implement the classical Boolean logic gates, it often takes more overhead. Just as if you try to do a classical algorithm using reversible, you know, logic, that often, if you just count the number of gates you need, or equivalently the amount of time it's going to take, that's actually harder or longer than it is to run a standard, you know, Boolean logic algorithm in the way that we commonly do. So that's what I meant by we certainly do no better, and we often do worse. Yeah.
Okay, thank you for that. I hope Gibbs was listening and understood that part. Then Fatima says, "Hi, Professor Oliver. Thank you for this great presentation. Since quantum technologies are not that widespread all around the world, finding research opportunities is very hard for undergraduate students like me. However, I want to pursue higher education and I assume research experience will be beneficial for getting accepted to reputable programs. What is your advice to undergraduate students in this situation? Thank you."
Yeah, thanks, Fatma. That's an excellent question. And my response, I think, would be um, related to that quantum engineering chart I just showed, which is that developing quantum computers in the future is going to require basically people from nearly every department at an institute, right? And so my suggestion would be to study what interests you the most, right? Because you want to do something that you really are interested in, that you love, and just do the best at it that you can, right? Study hard, get good grades, and then when you go to graduate school, then find a place where they're doing quantum in a way that you're interested in. Yeah, and doing maybe the modality that you like the best. And I think that's the best way. But the point is just study what you enjoy, whether it's engineering or science or math. I don't think that matters so much. What matters is that you're really passionate about it. You do the best you can, and I think that you will find that your talents can be applied to the development of quantum information technologies in the future.
Thank you for those words of encouragement. I think a lot of us need to hear that. So Tapioa says, I have a question regarding the slide on modalities. How is a cavity recognized as a modality, if not for NV center qubits for quantum sensing? I guess I'll ask Tapioa to unmute and come through and ask his question directly in case I don't ask it the right way. So Tapioa, if you are listening, do you mind unmuting and asking Professor Oliver directly your question? Okay, so perhaps he is not able to ask directly. So I'll just try to ask the way that it's phrased in case we are able to answer him. So he's asking, how is a cavity recognized as a modality, if not for NV centers for quantum sensing? Is it possible to incorporate or couple the cavity information into a superconducting transmon qubit? I think he's talking of building a hybrid quantum device. I think
Yeah.
at a high level, what are your thoughts on hybrid quantum devices?
Yeah, so thanks for the question. Of course, that chart falls short in a few ways. And one is that I don't include photons explicitly, even though photons are a modality that is currently being used for quantum computing. It's hard to place it on that chart because it's probabilistic. And in fact, it's new enough that there aren't as many demonstrations available, although more and more, I think we're starting to see them. So that's one thing. The other is that cavities, particularly superconducting cavities, which maybe this is what you're thinking of, those superconducting cavities can be used to store photonic states, right? And they can be, small cat states, as they're called, or they can be, larger, more complicated, continuous variable states. But basically what that is that the quantum information is stored in the photon field, the electromagnetic field of this cavity. And then typically a superconducting qubit is used to manipulate the quantum information in that cavity. Now the cavity by itself is if it's a linear cavity, which it probably is, then controlling that is difficult. But if you have a superconducting qubit, which, as we've talked about, is a little bit nonlinear, or has a nonlinearity, you can couple that into the cavity, and that makes the cavity slightly nonlinear. And because of that, that leads to the ability to control it with a qubit. So in this case, the superconducting qubit is actually used to control the electromagnetic field in the cavity, which is itself the data qubit.
Okay. Get up the question. What does the benchmarking of quantum chips entail?
So benchmarking, that's a great question, and I didn't have a slide on it. But basically, we care a lot about how good or how well we can implement a gate operation is. And so there are a number of techniques that we use to quantify the goodness of a quantum gate. Now, some of them are quite precise, but they require a lot of measurements. One example of that is called process tomography. And you can think of process tomography as I have a gate and I'm going to feed it all possible input states, well, a basis of input states, not all possible, but a basis of input states. And then I'm going to measure along a basis of output states, right? And so, think of it, you've got some unknown object and you're going to shine a light on it from each direction, from the X direction, the Y direction, the Z direction. And in each case, you're going to look at the shadow on the wall. And by looking at the three shadows, you can reconstruct what that object is. There's a similar idea quantum mechanically where you're using different input states. Now, again, a basis of input states. And then you look at a basis of output states and you look at all combinations and then reconstruct what that gate operation must be. So that's one way to do it, but it's very expensive. It takes a lot of time. And if you had more than say 3 or 4 qubits, it's almost impractical to do it. So the other way that we do it is by randomly throwing gates at the qubit. And then we look on average, what is the error that we get? And the advantage of that is that it's not as, it doesn't scale as poorly. It scales in a better way. And the other, I would say, but the disadvantage, again, no free lunch, is that you get an average error, but you don't get the specific error, right? So, on average, my gates have so much error, but in total, which ones and, from which directions are those errors occurring, we don't really get that information.
Okay, then Niraj says, thanks, Will, great presentation. Would 3D integration invite more crosstalk noise? I was wondering why transistors, for example, have made the jump to 3D and whether this would be popular in quantum computing as well.
Okay, yeah, so in fact, of course, it all depends on how you design and the details matter, but 3D integration actually offers the opportunity to reduce crosstalk noise because of many things. But one is that if you have these through silicon vias, they can act like via walls, so they can act as a shield in some sense. So in fact, the 3D integration affords new opportunities that you just can't get in 2 dimensions, in addition to just routing the wires. So, transistors are also, in some sense, making this jump to 3D, and they do it monolithically in some cases, or they do it with chiplets, right? Putting multiple chips onto another wafer. As Moore's law scaling comes to an end for transistors, it's not the end of the road for performance improvement. It just means that we're not going to scale the transistors smaller than a nanometer or 2. Just can't do it, right? But that's not the end of the road. We can use 3D integration or chiplets or other technologies to gain other performance advantages, right? So that's the classical story. And I think in quantum, it's a much more practical issue right now that it enables us to get the wires where they need to go. And it may also have some advantages for reducing noise.
Sounds good. And I've got a couple more questions. Some of them are going to be fast. We want to perhaps take you through a lightning round and learn more about you and have a bit of fun to close this off. But before I go there, I was going to ask you a question which I think is very important for this community. When you look at progress in the quantum tech ecosystem, besides the developments that are happening very fast in hardware, where else do you think a lot more effort needs to go so that perhaps we direct our energies there?
Well, certainly from my perspective, I think that developing quantum algorithms that provide advantage in the nearest possible time frame is quite important. You know, right now, there's a lot of interest, of course, from companies. There's a lot of investment from governments worldwide. But of course, the companies are in it because they want to generate revenue someday, right? And if they need to wait 10 or 20 years for an error-corrected quantum computer to come along before they have a commercializable algorithm, that's a long time to wait for a company. And so I would say that in addition to, of course, building hardware with larger qubit counts and better quality qubits, that's also extremely important, that, you know, in addition to improving the hardware, finding commercializable algorithms, particularly those before we have full fault-tolerant error correction, is very, very important, because we want to get into this commercial cycle where this year's revenue is generating next year's development. And we're not there yet. I think that we still need to develop, we need to put a lot of work into developing algorithms.
Sounds good. Thank you so much. So I would like to take you through a lightning round. It's always a fun activity we do with our speakers to just learn more, a bit more about them in terms of personal level and, you know, some of the exciting things that may just come out of that. So let me quickly run through that. Okay, so you can give us the shortest answers possible, because we just want it to be quick and to also be fun. So perhaps one of the first one would be, which book are you reading outside quantum at the moment?
Oh, I'm sorry. Could you repeat that? I didn't quite catch it.
Okay, which book are you reading outside quantum at the moment?
Oh, which book am I reading?
Yes.
Ah, okay. Well, that's a good question. So I'm reading a book by Jared Diamond, and I'm trying to remember the title of it, but it has to do with you know, the historical development of cultures around the world. Yeah.
Okay, and I promised people that you were going to tell us about music and how it led you to quantum. Would you briefly just talk about that?
Could I say something about?
About music
Oh.
and how it led you to quantum tech.
Yeah. So, you know, I thought for a long time that I wanted to be a sound recording engineer, you know, making records basically. And I had a, you know, I was in a band, and et cetera. But I think where that led me was that I was very interested in digital signal processing, right? And then that led me to think about computing and how signals are actually processed in a computer classically. And from there, then I got interested in quantum computing. And so that's basically how I got from music to quantum computing.
An interesting journey. Any perhaps a quick highlight on how your experience and exposure in Japan has helped you in this life of research or at a personal level?
Yeah, well, you know, I was I wanted to be an exchange student in high school, and I was set to go to Switzerland because I love to ski. And unfortunately, I don't speak any German. And at a very late stage of the arrangement, the Swiss side realized I don't speak any German, and they said, well, we can't take the student. And so the organization that was helping me, Rotary Club, do this exchange program, they said, well, the only place we have left is Japan. And so it was by complete chance that I went to Japan. But I must say that it has influenced me in many ways since then. And, you know, it turns out, I mean, just, you know, completely random, I guess, but that the first qubits, the first working qubits in 1999 were developed at NEC by Yasu Nakamura, Joshen Sai, and Yuli Man. And you know, I have visited and worked with that group many, many times over the past 20, 25 years. And I feel like the time that I spent in Japan in high school, and then I studied more in college and ended up living there for about 3 years, you know, has connected with my work in quantum computing quite heavily, even though, of course, nobody knew it when I was 16 years old. So I certainly did. Yeah.
Sounds interesting. What is your favorite symbol or not so simple technology tool that you are relying on at the moment?
Which technology do I rely on?
Yeah, which you think makes your life much easier, which we can perhaps
Oh.
copy.
Well, certainly using these digital electronics, right? An arbitrary waveform generator, but these microwave electronics that I was talking about in the talk, you know, none of this would be possible if we didn't have that. And these were, I would say, perfected over the last 30 years, in part due to gallium arsenide development in the 80s, radars, cell phones, you know, all of these technologies have grown up based on, you know, this research that was done in probably the 70s and 80s, in these hemp-like transistor structures. And we totally rely on it today, as well as the software to control these qubits that's run on computers like we're watching this Zoom right now. You know, we are able to do these experiments because we stand on the shoulders of the people who developed all of this technology, right? And not to mention the refrigeration. Yeah, that thankfully we can just buy dilution refrigerators today, because, you know, 30, 40 years ago, graduate students toiled really hard to make these things work. And today they're just off the shelf. So many technologies like that we rely on.
Sounds good. And the last one will be, if we had a capable quantum computer today, which problems would you personally, deploy them to solve first?
Well, you know, in the near term, I think it will be mostly interesting physics problems that are difficult to calculate on a classical computer. These may be related to topology or mathematics, states of matter, many-body states of matter. In the longer term, I think where quantum computing will really shine is in the simulation of materials and chemistry. So quantum chemistry is a field today that uses classical computers to do the best they can on quantum problems. And of course, they do very well. But there are still problems that are hard, even for the great quantum chemistry we have and the computers we have. And I think quantum computers will help us tremendously there to understand, for example, reaction rates in larger molecules. And when we understand them better, we'll be able to create new materials or new chemistries, chemicals, by design that do or have functionality that we just are dreaming about today. So I see these as really two of the directions that quantum computers will go.
Wow, thank you so much, Will. I can't thank you enough. And I wonder if ever people want to keep in touch with you, what's the best way to connect?
Oh, yeah, I think by email is a great way to connect for sure.
Sounds good. Thank you so much. And if you still have a bit more time, we usually host a cocktail after this. Lorraine, I think, has shared the link in the chat, which we normally use, and we're inviting everyone else as well to come and join us for the cocktail, where we have one-on-one conversations and just to take this conversation beyond the Zoom platform. So thank you so much, Will. I can't thank you enough for this meeting, and all the best, and with the hard work that you're doing to move quantum forwards. We will also do our part and try to get involved in the algorithms and make sure that we can make the most use of the available hardware.
Yeah, well, thank you very much for everyone for your attention, and thank you for the invitation, Farah. I really enjoyed it. And yeah, I'll jump over to the link here in just a second.
Thank you.